In this video, we're going to continue looking at the sarcomere and muscle contraction, and we'll specifically look at the relationship between length and tension. We'll define the following terms: tension, contraction, twitch, motor unit, and myogram. We'll interpret a graph of the length-tension relationship and describe the anatomical basis for that relationship. We'll interpret a myogram of tension versus stimulus frequency and explain the physiological basis for TREP, summation, tetanus, and recruitment. We'll compare and contrast isotonic and isometric contraction. Muscle contraction occurs when actin and myosin fibers slide across one another and shorten the sarcomere. For efficient muscle tension to be generated, the proteins must overlap, but still allow room for movement. We saw this in previous videos, that the actin here and the myosin here will slide against one another. The actin doesn't shorten and the myosin doesn't shorten. Instead, the actin will slide closer to the midline, and as it does that, this kind of length between the myosin and the Z line will shorten, and the I band will shorten because the overlap increases. The actin doesn't shorten and the myosin doesn't shorten. They just overlap each other more. So to have efficient muscle contraction, we have to have some overlap. But if we have too much overlap, the myosin will bump into the Z line. That's not efficient. If we don't have enough overlap, there won't be any area for the myosin to grip on the actin. So we have to have some overlap. A little bit of overlap is ideal. So we want a resting position where there's some overlap, but still also some room for movement. At the optimal length of overlap, the muscle can generate a maximum amount of contraction force. At this length, the myosin heads can get a good grip on multiple active sites, and the sarcomere still has room to shorten. So here we have this overlap. Those myosin can still move the actin. There's still room for the actin to move inward. There's still room in this I band for shortening, and there is enough area for myosin heads to grip on actin, to get a good grip, to pull that actin towards the midline. Skeletal muscles are normally kept within this optimal range through the placement of bones, joints, ligaments, and tendons. So those help keep our muscles in place. If muscles are overstretched, the contraction force is decreased. In this situation, myosin heads can't get a good grip on the actin active sites because there's a minimal overlap. The more stretched out fibers are, the less likely a strong contraction force can be generated. So here we have a good overlap. So we can get a maximum amount of tension when our overlap is ideal. If that overlap expands, so as the overlap gets less, so less overlap because we've expanded the sarcomere, now there's no overlap, we can't make any cross bridges because there's nothing for the myosin to grab. So if that muscle gets overstretched and the sarcomeres stretch out, there's no overlap with the myosin, there's nothing for it to grip. So if it's trying to power stroke, it can't do anything because there's no actin for it to bind. We need at least some overlap. So we need overlap to get our maximal strength here. If we stretch out the fibers, we don't have any overlap and we can't generate a force. Same if the fibers are too compressed. If they are already fully contracted, fully overlapped, then there's nowhere for them to go. They can't overlap anymore, and so we can't generate any tension when they're already completely overlapped. There's no more room for them to overlap anymore. The myosin has already reached the end, and everything is bumping against each other. So in this situation, cross bridges can form, but contraction can't occur because the sarcomere has no further room to shorten. The more compressed a muscle is, the less likely a contraction can occur. A myogram is a recording of the force of a single muscle fiber twitch response over time. So this is a single stimulus over time. How much muscle force do we generate? So this is a myogram. After a stimulus is applied, here at time 0, there's a latent period where we're not seeing any tension. So we don't see any tension during the latent period right here. Tension stays low. That's because during this time, the action potential is sweeping across the sarcolemma, the calcium ions are being released from the sarcoplasmic reticulum, and that all takes time. It's a very short amount of time, about 5 milliseconds, but it does take time for the action potential to come across, as we saw in previous videos, for the calcium to be released, as we saw in previous videos, that takes some time. After calcium diffuses from the sarcoplasmic reticulum, it binds to troponin. That alters the position of tropomyosin. That will expose the cross-bridge binding sites. Once those cross bridges form, then we can get contraction. So in the latent period, we have action potential and calcium release. In the contraction period, then we have the actin, myosin cross bridges. Those are forming. That will shorten the sarcomere. And that's where we get muscle contraction, is those cross bridges sliding across one another. When calcium levels fall, as when calcium returns to the sarcoplasmic reticulum, the troponin and tropomyosin again cover the actin binding sites, prevent formation of further cross bridges, and we get relaxation. The sarcomeres will return to their original length, and tension force decreases as muscle relaxation occurs. So tension goes down as the muscle relaxes. That contraction period is when tension is going up. That's when the muscle's contracting. So the sarcomeres are shortening during contraction, and then they're releasing during that relaxation. The frequency and intensity of muscle contraction is fine-tuned by two factors: how many motor units are activated, and what's the frequency of their stimulation. So how many nerve fibers are we stimulating, and how fast are we stimulating them? And we can look at those as some relationship graphs. Individual muscle twitches occur when a muscle fiber has time to fully relax between stimuli. So this is like the last picture we saw, except we have lots of them in a row. So muscle twitches in a row. The previous picture we saw where it looked like this, that's one muscle twitch. If we just twitch one time, one fiber one time. This is multiple stimuli here. So we would generate the stimulus here, not there. We have that latent period in there, remember. So individual muscle twitches occur when a muscle fiber has time to fully relax between each stimulus. When muscle fibers are allowed to fully relax, each twitch may reach the same maximum force, and there may actually be a slight increase. So if you look at these are actually getting more force, and then they kind of plateau here. But more force. How they're getting more force is a process called TREP. What happens is when we increase that, we don't get all the calcium back into the sarcoplasmic reticulum. So if we have more calcium out there, then we can get a little bit stronger contraction because we have more concentration of calcium. Even though we're allowing the muscle to fully relax, all the calcium may not get back in there. That's called TREP. TREP means stair step, and it looks kind of like a stair step. So when the frequency of stimulation speeds up, an increase in force may occur. Some calcium from the first response is still out of the sarcoplasmic reticulum when the next stimulus applies. Wave summation occurs when a muscle fiber is allowed to partially but not fully relax before another stimulus is applied. Remember, with TREP, we had full relaxation. So we're all the way down relaxing. We get some increase in contraction force because of that, tension, because of that calcium still being in the out of the sarcoplasmic reticulum, but we still allow the muscle to fully relax. If we don't allow it to fully relax, and we keep applying a stimulus before it's relaxed, then we get what's called wave summation, because it looks like a wave. So it looks like a wave moving up. And we get more force because not only are we keeping that calcium out there, but we're not allowing it to fully relax before we apply another stimulus. So that's called wave summation, because it looks like it's getting bigger as a wave. As the frequency of stimulation continues to increase, so let's say we're applying the stimulation really rapidly. We'll get a wave summation that's no relaxation period, and so we get the maximum amount of tension that that muscle can generate. So as the frequency of stimulation continues to increase, the force will also increase to the maximum allowed by the structure of that particular muscle. When that maximum force is achieved, incomplete tetanus results. This picture doesn't show incomplete tetanus. Incomplete tetanus is kind of a combination of wave summation and tetanus. It would look like this. It's not complete yet. It still has a little bit of that wave summation, but it is approaching it. Complete tetanus occurs, and that's what we have here. Complete tetanus occurs when the frequency of stimulation is so rapid that the relaxation stage is completely eliminated and the muscle sustains its maximum tension. It's rare in real life situations that never occurs in a healthy cardiac muscle. Tetanus is not plateau. I should put that on here. Is not plateau. It looks similar, but plateau was an action potential. This is a measure of tension. Plateau was a measure of electrical charge. Tension is we're applying forces at stimuli and we're not allowing the muscle to contract. So this is a measure of tension, force, not of electrical charge. Plateau is a measure of electrical charge. Also, complete tetanus is not the same as a muscle cramp. Cramping is caused by dehydration, mineral deficiencies, or nerve and blood insufficiencies, not by the frequency of stimulation. So those are also different things. So tetanus can be physiological if we're sustaining a contraction, but it's not typical. Typically, we're going to use wave summation and probably even more typically TREP, but tetanus is a possibility. There is also, if you've taken microbiology, there is also a bacteria called tetanus, and that will cause muscle contraction, but again, not physiological contraction. That is a very painful contraction of all of the muscles, and that's why we're vaccinated against tetanus, so that we don't have the risk of that bacteria contracting all of our muscles and causing a very painful situation. A motor unit is one motor neuron and all of the muscle fibers it controls. So here we have two motor units in this picture. So we have the motor neurons coming out of the spinal cord, and here we have their axons, and we'll talk more about axons in the next unit. And so here we have red motor unit, number 1, and you can see that it's innervating this fiber. We've got red going to that fiber, and we have red going to that fiber. So two fibers for that one. Motor unit number 2 is blue, and it's innervating this one. It has neuromuscular junctions for that one, this one, and this one. So 3 on that one. Obviously, this is a schematic. Typical motor units would have on the order of hundreds to thousands of muscle fibers typically. However, it's going to vary based on location. The number of muscle fibers per neuron is very small where precise movements are needed. Your fingers and your eyes, very tiny muscles, very fine control. So not a lot of fibers per neuron so that we can be very precise. However, where you have very large, powerful muscles, you don't need a lot of fine control, you need power. And so a lot of innervation of fibers by the same axon in those areas. So the back muscles, the thigh muscles, the very large muscles will have more fibers per neuron in those motor units. Stimulation of a motor neuron to threshold stimulates all of its associated muscle fibers to contract completely. It's an all or nothing response. If you send a electrical signal, a depolarization down motor unit 1, both of these fibers will contract fully. If increased force is needed, additional motor units will be recruited, but the response of each individual motor unit is still all or nothing. So let's say you stimulated motor unit number 1 with the action potential and you contracted, and it was not enough. You can then activate motor unit 2, stimulate its muscle fibers, all or nothing, and increase your response. That's called recruitment. So we're recruiting them. So that's recruitment. You've experienced this. Think of if you've ever gone, I don't know if these are very common anymore, but you've probably experienced it with other things. If you've ever seen any of those foam bricks that look like a brick and you went to pick it up and you thought it was going to be heavy, so your brain recruited a bunch of motor units, and you go to pick it up and it's actually very light, and then you overcompensate because you thought it was going to be heavy. That's an example of recruitment. Or the opposite way, you thought something was going to be light and it was actually heavy, and then you're like, you try to pick it up and you're like, oh, and you have to recruit more. So our body recruits based on what we perceive the needs are going to be, but we can also adapt once we start lifting something, and either it's heavier or lighter than we anticipated. So with recruitment of additional motor units, the force of contraction of the whole muscle increases, but the maximum force generated by each individual motor unit doesn't change, because remember, when you stimulated one motor unit, it was all or nothing. So you're going to generate a larger contraction if you stimulate 10 motor units than if you stimulate one. But each motor unit, once it's stimulated, contracts fully all the way, all or nothing. Muscle tone for posture and body support is maintained by activation of alternating motor units in a muscle. So in that case, the muscle has to have some relaxation. It can't sustain like tetanus all the time. So it will contract, and then another unit will contract, but the first one will relax. So it's kind of passing that, and then they'll go back and forth. So they get a chance to relax, and the other one gets a chance to contract. By rotating that load, muscle tone can be maintained without fatigue. An isotonic contraction occurs when a muscle shortens because the force of contraction is stronger than the load. Isotonic means same or equal tone or stretch or tension. So same tension. In order to keep the tension the same across the muscle, the muscle will shorten to allow that muscle to maintain that consistent tension. So to maintain a tension, you'll shorten the muscle, and that's going to generate a movement. So with isotonic contractions, you get movement. Isotonic. Because the tension is staying the same, but the muscle will shorten. The word concentric comes from Latin terms con, which means together, and centric, which means center. Concentric contractions pull a muscle towards its center, shortening it. So here we have concentric contractions, and we're moving towards the center of the muscle. See, it got bulkier in there because we contracted it. So that's concentric, isotonic. Isotonic contractions may also be eccentric. Eccentric contractions occur where the load is greater than the maximum tension the muscle is capable of, therefore elongates instead of shortening. So in this case, it elongates and gets longer, and it's less bulk in the middle. Because you can lift up the weight, but at some point you have to put the weight down. So, and you may consistently lift and put them down. So you get both the concentric, because there is a muscle conditioning where you can hold the weight. But if you consistently contract and relax, then you can condition that muscle to adapt to that. However, with that elongation, if it elongates too much, it can overstretch and damage the muscle. Because remember, we talked about sarcomeres. If you overstretch, then you can't get that grip between the actin and the myosin, and that can cause damage to the muscle. The word eccentric comes from Greek terms ek, which means out of, and kentron, which actually it has the same centric as the previous word too, which means center. Both meant center, but out from the center. So we're moving out, away from the center with an eccentric contraction. So eccentric contractions pull a muscle out from its center, lengthening it. An isometric contraction occurs when the muscle does not change length and the tension produced does not exceed the load. So with an isometric contraction, there's no movement. These contractions are used to stabilize bones without moving them, such as shifts in balance to oppose the force of gravity and stabilize the body. The word isometric comes from the Greek words iso, which means equal, and metric, which means measure. I'm not going to quiz you on the meaning on the Greek and Latin roots. That's from medical terminology, but it helps you kind of if you understand what it means, what the roots means, you don't have to memorize it. You can logic it out. You can work out what it means from its roots and its prefixes. So I go through those to help you learn what the word means and be able to recognize what the word means, so you don't have to memorize the word. You can kind of understand it. Isometric contractions occur where tone may change, but where muscle length remains the same. So isometric is same length. Within muscle contraction, the rate of contraction or the velocity varies inversely with load. As the load on a muscle increases, the muscle contracts more slowly. As the load decreases, it contracts more quickly. I'm sure you've all experienced that. So if you've got a harder, heavier load, your muscle will contract more slowly. If it's a very light load, you can contract it very quickly. The extra time to contract against larger loads is due to the time necessary for recruitment. So remember, with a larger contraction, you need to recruit more motor units, and so that takes a little bit of time for that to occur. All right, in the next video, we're going to look at metabolism.